I want to talk about calculating the width of the center bright region when you send light with a single wavelength through a single narrow opening with a given width. So this is an example of Fraunhofer diffraction. And for Fraunhofer diffraction, we get minima in the diffraction pattern that occur where the sine of the angle to each dark region is equal to an integer that's non-zero times the wavelength divided by the size of our aperture. Well, for the bright region, what we would see is we'd have to go up to an angle with an m of +1 and down to an angle of m equals -1. And when this opening is some distance L away from our viewing screen, then we're going to have a height y above and below the exact center of our bright region that we can find using a little bit of trigonometry. So what we would see is that our angle to our dark region forms the angle of a right triangle where the adjacent side is our distance from our aperture to our viewing screen, and our opposite side is our distance y1 from the very center of the bright region to the center of that dark region. So that makes up a tangent. So our distance y1 would be equal to the distance from our viewing screen to our aperture size L times the tangent of the angle to that first dark region. Now, as long as we're dealing with small angle, and in physics, small angle means less than 10 degrees, y1 could just be said to be equal to L times the sine of theta1 instead of the tangent of theta1. Because if we're small in angle, cosine's going to be close to 1, so sine and tangent are going to be really close to each other, and they'd also be about the same as the angle itself too, which is the more common way in physics we make that approximation. So that means then our distance above and below the center would be equal to the spacing from the openings to our viewing screen, L, times the wavelength of our wave divided by the size of our aperture. And the width then would be twice that distance y1. So we'd be looking at a width for a spot of 2 times our separation distance L times our wavelength lambda divided by our aperture size. So let's choose a distance L, which is roughly the length of this whiteboard that I have behind me, 1 meter. We're going to use a wavelength of 633 nanometers, which conveniently is kind of in the middle of the red end of the spectrum. And the width we're going to use is 126 microns, which would be 1.26 times 10 to the negative 4 meters, or something about like a few of these right here twisted together in making a rope in terms of a diameter. So if we multiply 2 times a meter times 633 nanometers is 6.33 times 10 to the minus 7 meters. Divide by 1.26 times 10 to the negative 4 meters, we get a width of about 0.0100 meters, 1 centimeter, which is about the size of the spot right here at this end of the projector, or this end of the screen, based on, like I said, the opening size that I mentioned a moment ago. Thanks for watching.